Okay, there we go. So this time I'm going to be talking about unsupervised machine translation. And this is a very interesting topic overall. My mouse has disappeared. And if you've done the reading, you can see that it's to greater or lesser extent practical for some varieties of text-to-text translation, but I think there's a lot of other applications as well, maybe including with speech or other things that we're going to be talking about in the future. So I think the underlying technology is interesting and worth discussing and knowing about, both with respect to the techniques and the limitations and other things like this. So I'll go ahead. So conditional text generation, which we've talked about. Hang on 1 second, let me move that out of the way. So conditional text generation, basically we're generating text according to a specification, like I talked about before in the sequence models class. So, you know, we have our input X and our output Y, where it could be for machine translation, image captioning, summarization, speech recognition, etc. And so the way we model this is using some variety of conditional language model, like you know, sequence model, like the ones you're training for assignment 2 with our encoder and our decoder. And the way we traditionally estimate the model parameters here is using maximum likelihood estimation to maximize the likelihood of the output given the input. And generally, this needs supervision in the form of parallel data, usually millions of parallel sentences. So what we're going to ask about in this class is, what if we don't have parallel data? So just to give a few examples of this, these are old slides. I modified the slides, but they disappeared somewhere, I guess. So I'll try to fill in the blanks. But so we have parallel data. What if we don't have parallel data? So for example, let's say we have a photo of a person's face or something like that, and we automatically want to turn it into a painting, you know, to put on your wall and display or something like that, or turn it into a cartoon because you want a picture of yourself for your social media profile in a cartoon or something. So unfortunately, we don't have tons and tons of data for this, but we do have tons of photos and tons of paintings. So we have lots of input X and lots of output Y, but very few pairs of input X and output Y. We could also do other things like transferring images between genders or between ages or something like this. I think you've seen apps that might do this. Text from impolite to polite. So, you know, correcting the formality, transferring a positive review to a negative review or vice versa, or doing something like machine translation. And I actually modified this to give a few other examples, like some really, but the slides disappeared. Some really interesting examples are, what if we had an ancient language or a cipher where we didn't actually know what it was, we didn't have any paired text, but we wanted to decipher this old text and replicate and like understand what it meant in the modern language. So that's another thing that we could do with unsupervised translation. So another question is, couldn't we just collect or generate data for these tasks? And to some extent, the answer is, you know, yes, we could for some, but it could be too time-consuming or expensive. And it can also be difficult to specify what to generate or even evaluate the quality of generation. So if we said, generate this text like Joe Biden said it, many people here, you know, don't know what Joe Biden sounds like enough to be able to even do this in the first place. So, you know, it's difficult and underspecified, and finding people who'd be able to do that would be difficult. And because of this, this often doesn't result in good quality data sets. So in unsupervised translation, the basic idea is we have some sequence task, you know, translation being the stereotypical example, but it could be any of the other ones that I talked about, where we instead of using like monolingual data to improve an existing MT system trained on parallel data or reducing the amount of supervision, we'd like to talk about, can we learn without any supervision whatsoever? So there are some core concepts in unsupervised MT, and these core concepts include initialization, iterative back translation, bidirectional model sharing, and denoising autoencoding. And actually, from the point of view of unsupervised MT, in some cases, people have also used older statistical machine translation techniques instead of neural machine translation techniques because they were more robust. I'll talk a little bit about what statistical MT means because we haven't really talked about it here yet. And I'll also explain a little bit about why it is more robust and what we could do to also improve robustness of neural MT as well. So for step one in initialization, basically a prerequisite for unsupervised MT is that we start out with an initial model that can do something, that can do some sort of mapping between sequences in an appropriate way so that we can use it to seed a downstream learning process to do translation. And it basically adds a good prior to the state of solutions we want to reach. And the way this is done is by using approximate translations of subwords, words, or phrases, usually. And the way we take advantage of this is we take advantage of the fact that the context of a word is often similar across languages, since each language refers to the same underlying physical world. And what we do is we rely on unsupervised word translation. And I talked about this a little bit 2 classes ago. I also called it bilingual lexicon induction. And the basic idea is that word embedding spaces in 2 languages are isomorphic. And what I mean by this is if you take an embedding space from one language, like let's say English, an embedding space from another language, let's say Spanish, we can learn some function that isn't overly complicated that allows us to map between these 2 embedding spaces. So for example, we might run a model like word2vec or any other kind of word embedding induction technique to embed individual words in embedding spaces. And then we learn mapping between them, like an orthogonal, like a matrix transformation, Wx equals Y, maybe with some constraints, like the W is orthogonal, which basically makes the embedding mutually, makes the embedding like bijective, so you can mutually map between one embedding space and another embedding space. And we hope that by applying this transformation, we will end up with something where the words in one embedding space or the words in both embedding spaces, if they're close together, the words are similar semantically or syntactically. And this is hard to believe that this would actually work. I actually remember going to a presentation in ACL, I think 2016, where this method was proposed. And I was like, there's no way this could possibly work because you're assuming that, you embed words and then just transform them in some way and the distributional properties cause them to line up. In fact, it does work better than you would think it would. And there's a couple reasons for this. One reason for this is that in addition to distributional properties, a lot of the word embedding techniques that are used in these mappings here also take into account like subword information. And then if you're mapping between like English and Spanish or English and German or something like that, a lot of the words have similar spellings, and that can give additional indication about whether the words are similar. Another reason is like words like gato and cat are both common. And common words tend to map to common words, uncommon words tend to map to uncommon words. So you're also basically implicitly using word frequency information in the mapping. And frequent words in word embedding spaces often tend to have larger norms because they're updated more frequently. And so that kind of implicitly gets added into this calculation as well. So there's a bunch of things working for this. Nonetheless, it doesn't work perfectly. It works kind of well enough to do something. And in the case of initialization, that's mainly what we're looking for. We're mainly looking for something that starts us out in some sort of reasonable space. Yeah.
What if the words in the two domains are not one-to-one?
What if the words in the two domains are not one-to-one? Or what if the words in the languages are not one-to-one? So to give an example, let's say we're mapping English to Turkish, where in English, a single verb has, one or five conjugations, and then in Turkish, it has like 80. The answer is it basically doesn't work. It doesn't work. It doesn't work very well. So that's another thing that you need to be concerned about. But if the morphology is approximately the same, it can still do something. And the later steps of the unsupervised translation pipeline can also help disambiguate like ambiguous words and other things like that. So yeah, I saw another hand.
So I want to ask that if there's no parallel data and the two languages don't have like same words, don't have the same subtoken to get any sort of mapping between words, and how is this like expected to work? Like, you can just say that frequent words in two languages will probably be they can be mapped, but which frequent word matches to which one?
Yeah, so it's a combination of words being frequent and words being words appearing in the same context. So for example, just to give an example, proper names don't work particularly well for this method because especially if you have like a Japanese newspaper and an English newspaper, the proper names mentioned in the English newspaper tend to be English names, and the ones in the Japanese newspaper tend to be Japanese names, for example. However, there are these clusters of proper names, and proper names have a certain frequency profile, and they tend to cluster together. So at the very least, you should be able to get the fact that things in this cluster are proper names, for example. And that, like, I think intuitively you can see how that would be universal across languages, more or less. So you can get at least that close. And then there's other things like if two languages have determiners are almost always like the most common thing. So you could map determiners between languages and get them right most of the time and stuff. But completely unsupervised methods work kind of okay, but not really well. Yeah. Also, an auxiliary point is that there's very few languages in the world where you don't have any dictionary whatsoever. If there are languages in the world that don't have a dictionary, they also probably don't have written text that you could learn word embeddings from. So completely unsupervised, you might not need it, but you might want to do something with like just a dictionary. And so another thing that's commonly done is another way to do this distribution matching or to learn this distribution matching is basically to have an adversarial objective. And the adversarial objective, basically what it does is it tries to prevent a model from being able to distinguish between this X times W and Y. So the idea is you want to move the spaces so close together that like a sophisticated neural network or some sort of discriminator is not able to distinguish between them. So that's the actual mechanism for doing the distribution matching. Another thing that is commonly done, which I talked about 2 classes ago, but isn't included in the slides here, is you get an initial first pass where you find like several points that you're very confident in, like several points that are mutual nearest neighbors of each other, but don't have other close mutual nearest neighbors. And you use those as basically pseudo supervision, and then create a supervised model that tries to make sure that those get mapped as close together as possible while making others farther apart, and do an iterative process where you gradually like increase the number of words that are mapped together, and that further improves accuracy. Now, if you have like a small amount of supervision, if you have like, I don't know, 50 words in a dictionary, you could use that. You could use that to do supervision directly without having to do the unsupervised distribution matching at first. And in fact, two papers were presented at basically the same time. One was a paper on completely unsupervised mapping. Another was a paper where they only used numbers. Like numbers were the only thing that they used across the language, because numbers tend to be written in Roman characters in many languages in the world. So, sorry, Latin characters in many languages in the world. So because of that, you could use just that as supervision, and then that would get you a long way too. So if you have a dictionary, that gives you better results usually, even a small one. Yeah.
Does that actually really work? Because numbers, I feel like the information contained about that number in the word embedding is often not, like it doesn't really encode what the number actually is, just kind of that it is a number a lot of the time.
Right. But I think basically the idea is if you can get any supervision, it's better than no supervision, and you're still going to have like ideally some sort of distribution matching component in your objective anyways. So yeah. Yes.
With this method, do we still ensure that W is orthogonal?
That's a really good question. So if you have supervision, you wouldn't necessarily have to do that. We've done some work on unsupervised embedding induction, and it almost always helps to ensure that W is orthogonal, and it almost always helped us anyway to ensure that W was orthogonal, and it almost always helped us to not use anything more complicated than a linear transform. Like you would think you'd be able to throw a big neural network at it and it would do better, but like even in supervised settings, I guess the problem is too underspecified, and that didn't help very much. So, not to say it wouldn't ever. Cool. Okay, so the next thing is we pull out our favorite data augmentation method, back translation. And so we take, for example, French and back translate it monolingual data into English. And we take English and we back translate monolingual data into French. And so here we have parallel data. We have parallel data here, but what we can do instead is we can do like pseudo parallel data, which I'll talk about in a second. So next, I'd like to explain how we apply these methods to a non-neural MT system. And just to give a very brief overview, a one-slide primer on phrase-based machine translation. So this is what a lot of people used to do machine translation before neural MT came out. And it consists of 3 steps. First, the input, the source input is segmented into phrases. These phrases can be any sequence of words, not necessarily linguistically motivated, so they don't need to be like a noun phrase or a verb phrase or anything like this. Then you take out a dictionary and you replace, like the dictionary has translations of the phrases into the target language. Maybe it has, 10 or so candidates for each phrase. And then the phrases are reordered to get into the correct order. And this is a nice method for some reasons. And one of the reasons why it's a nice method is it's guaranteed to basically cover every word in the inputs and not do any, if the model is trained okay, not do any really, really crazy things. So if you guys are struggling with assignment 2 right now already, and you're getting your like low resource machine translation, neural machine translation system, it's probably doing things like repeating the same word 300 times in a row or something like that. A phrase-based machine translation system would not do this. It might give you a bad output, but it wouldn't, repeat the same thing over and over again or translate a sentence into like an empty sentence or something like that, precisely because it has to cover all the words and it can only use a fixed set of translations. So because of this, it has a strong bias to generate like non-nonsense, but it's also, not as powerful as neural MT, basically. So the segmenting into phrases is easy. The reordering is not easy, but possible. But in order to translate each phrase, you need parallel data for this. And that's a problem in unsupervised MT, of course. The way unsupervised statistical MT could work, which is also detailed in these two papers by Arteja and Lampel, is you learn monolingual embeddings for unigrams, bigrams, and trigrams. You initialize phrase tables from cross-lingual mappings of these embeddings. So basically, you initialize the phrases that could be used in a phrase-based machine translation system. And then you do supervised training based on back translation and iterate. So what this means is basically you take the phrase tables from cross-lingual mappings, you estimate a language model on the target language, and then you just translate all of the monolingual data. And after you've translated all of the monolingual data, then you can then feed it into your like normal machine translation training pipeline. And the key here is that you're inducing each of these phrase translations just by mapping embeddings of unigrams, bigrams, and trigrams. Cool. And what we can see here is that if we start out with the unsupervised phrase table and translate from French to English, we get a blue score of 17.5. And then as we add more iterations and translate and translate and translate and learn from the translated data, the score gets a bit better every time. So basically, it's this iterative process of recreating the data back translation in one direction, the other direction, one direction, the other direction in training. Cool. Are there any questions about this? Okay. So I'll go to the next one. So unsupervised neural MT, the way this works is we create a neural MT system. And actually, the exact same procedure could also be done for neural MT with the caveat that you can't create a phrase table. So you would need another method for learning the initial model. Because you can't like induce a phrase table from embeddings. So in addition to using that same procedure, there's one thing that you can do to improve the neural MT model. And basically the way it works is you take the encoder decoder model and you use the same encoder decoder for both languages. And another thing that you can do is you can initialize the inputs with cross-lingual embeddings. And the idea of what you do here is you train a model to output French, but you have the input be either French, so it's like an auto-encoding objective, or English here. So if you have this French token here, this is basically saying, I want you to generate French next. So the model is, basically guaranteed to generate French. But because these input embeddings are initialized with bilingual, like coordinated embeddings, the inputs look very similar. So it's like the inputs look similar. I know I want to generate French. So if we just train on this auto-encoding objective in the bottom, which we can do for monolingual data, it nonetheless learns how to translate, is the hope and dream. So we have a couple objectives. One objective is the denoising autoencoder objective. And so what we do is we take the target sentence, the source sentence, we map it into, sorry, so this is a denoising autoencoder. And what a denoising autoencoder does is basically we have a sentence in the source side. We add some ways according to this corruption function C. Oops. This corruption function C. So we move X into some other place C. We map it into a latent space, and then we try to regenerate the original X. And I'll give an example of this in a moment. And the other objective that we can use in unsupervised MT is back translation. So what we do is we translate the we translate the target to the source, and we use this as a quote unquote supervised example to translate the source to the target. And okay, sorry. So let me give a few examples here. If I can find some chalk. So one example of a denoising objective would be just to like cross off individual words here and to try to reproduce the original sentence from the crossed off words. So we set their word embeddings to 0 or something like this. And so that would be going from this X to the CX. And then we could just run a sequence model to try to take in this noised input and generate the output. So that would be one example. And in this particular case, what we could do is we could try to translate this into another language. And this translation could either be done with like a pre-trained model that we have already from our previous iteration of unsupervised translation, or it could be done with some sort of heuristic, like mapping the words into input. And I think I have a slide about that coming up soon. And so the reason why it works is, as I said before, cross-lingual embeddings and the shared encoder-decoder give the model a good starting point where translating from this is similar to translating from this here. And so then another objective that people use to further enforce this is an adversarial objective. And what they try to do essentially is you have an autoencoder example or a back translation example, and you apply an adversarial objective to try to force these two phrases together. So this is also similar to what they use in unsupervised like word translation, where you have a model and you try to get these encoder vectors to be so similar that you fool the model and it's not able to distinguish between them. Yes.
Is denoising what I'm putting similar in some ways to masked LLM sort of?
Yeah, so actually masked LMs are a variety of denoising autoencoding. It's basically a subset of denoising autoencoding objectives. Yeah.
How is it different from the multilingual learned in last class? Parallel data and some called unsupervised behavior.
Well, so here we're not using any parallel data whatsoever. So the back translation is, we're not using any real parallel data. All of the parallel data we have is obtained through like back translation, for example.
So for it to work from French to English, how does it work?
Yeah. So yeah. Sorry, I'm not used to using PowerPoint, and it's taking forever to translate.
What's the objective function?
Yeah. So basically, there's two ways that you can do this. The first way is with just using a autoencoding or denoising autoencoding objectives. So to take the example here, we have like I am a student, and and so if you have bilingual embeddings or something like that, where the bilingual embeddings got mapped close together, basically, you know, these word embeddings look the same. These word embeddings maybe look the same, and these word embeddings look the same. So overall, the vector looks the same. Yeah. And so, like, despite the fact that what you want to do is on the bottom, the vector, the light blue vectors on the top, if each of the word vectors looks similar, also looks similar. And then you can also do things like randomly masking out words to make it look a little bit like, basically to make the problem of autoencoding more difficult. And so you need to fill in more information. So when you move from this clean English over here with some blanked out words to French, you know, the problem also gets harder. So you kind of need to infer missing things or differences from this, but because you're doing denoising, it allows you to do that. For back translation is basically like what we talked about before. It's like more or less the same. So actually, perhaps a more important thing is the denoising of autoencoding objective. Yeah.
Wouldn't this lead to like more hallucination by the model? Since the noise is like, if you remove student from this and then you're asking it to reconstruct, I am a student, so I guess in the translation.
Yeah, so wouldn't that lead to more hallucination from the model? Yeah, basically, yes. I think it's going to be very hard to train a model that works perfectly through purely unsupervised translation. But the idea, one thing is that any mistakes in your one reason why back translation works in the first place is any mistakes in your training data tend to be more random than the actual correct training data. So as you refine the model more and more and get a better and better model, the hallucinations, because they're random, tend to get washed out, whereas the like correct translations tend to be reinforced because they're more consistent. So it still will hallucinate and make mistakes, but hopefully the idea is that hopefully they get washed out. It works. Yeah.
Just a little curious about why we can count the back translation method as a unsupervised method. Because yes, we do not directly use the supervised data during the training. The back translator was trained based on express data. So somehow that we use the supervised data, now it's that obviously. So I'm curious why we call it as unsupervised.
Yeah. So this slide is a little bit deceptive because this would be the example of like supervised back translation here. In unsupervised back translation, in the back translation in the unsupervised like MT paradigm, basically you don't use any parallel data. You just use a denoising autoencoding objective to seed your back translator and then use that to generate data. So you're never using any like actually parallel data. So basically you start out with just a model trained using monolingual data and denoising. Yeah.
So for the example that you showed before this,
Mhm.
so that was the print sentence to English is just dumping the inference check, right? There's no supervision for that part.
Yes, there is no supervision. Cool. Okay. So this is a graph from the original paper. I think there's a big caveat in this graph, so you need to be a little bit careful in interpreting it. But basically, the horizontal lines are an unsupervised translation model that uses lots of monolingual data, but no parallel data. the non-horizontal lines are a model, are the supervised translation model. And basically what they're showing here is with no monolingual, no parallel data, they're able to achieve scores of about the same level as something trained with 10 to the 5, so 10,000 parallel sentences. A big caveat here is that they didn't use any monolingual data in the supervised translation system. So if they did, the supervised translation system would probably be a lot better. But still, I mean, it's kind of interesting that you're able to do anything at all with unsupervised translation. So I think as long as you're aware of that caveat, it's kind of an interesting graph.
Graham,
Yeah.
was this data things like middle call?
Yeah, so another, so basically I'll go to the open problems in unsupervised MTs. So basically, this is exactly the problem that Alan was pointing out, which is unsupervised machine translation works in ideal situations. So basically languages are fairly similar, written with similar writing systems, large monolingual data sets in the same domain and match the test domain. So in this particular case, they were using data from the European Parliament. And it basically the data in the English and the French, or the English and the German, was from exactly the same distribution. And that really helps in like inducing the lexicon or doing translation. And so when you have less related languages, truly low resource languages, diverse domains, less monolingual data, unsupervised machine translation performs less well. And reasons for poor performance, basically small monolingual data in low resource languages can result in bad embeddings. So if we don't have lots of data in a low resource language, this won't work because the embeddings will be too poor to get a good initialization. Different word frequencies or morphology, like the English and Turkish example I talked about before. Also, different content makes things like back translation less effective at bootstrapping a translation model. So, for example, if you're trying to translate Twitter in one language and you have news text in another language, that's not like back translation is not going to be good for covering, you know, what is said on Twitter. So just in interest of time, I'll skip that one. But so there are some things that can be used to improve. So better initialization. Recently, people have been using things like cross-lingual language models or multilingual language models to improve the initialization of unsupervised translation models. So things like masked language modeling across languages. Okay, and so basically what you can do is you can train a single monolingual or bilingual, single multilingual language model as your encoder or both your encoder and your decoder, and use that to initialize the translation model. And this is good because you're initializing the whole model as opposed to just the input. And for various reasons, it's nice to have a single model that is trained on all the languages. And just to give one example, even in like Chinese or something that's written in an entirely different script than English, there's still lots of English words. So if you're training the English model and the Chinese model on tons and tons of monolingual data, the English words can also help anchor, you know, things into the same semantic space because they appear in various languages as well. Another thing is masked sequence modeling. So there's things like MAS, which basically they have an encoder decoder formulation of masked language modeling, where basically you mask out a piece of the input and you generate that masked out piece of the output. And recently, a model that lots of people have been using is this MBART model, multilingual BART model. And the way it works is basically you mask out words in the input, but then you generate all of the words in the output. So then you basically train this on tons and tons of data. It's a pre-trained model that you can then use to initialize your downstream unsupervised MT model. And I had some stuff about multilingual unsupervised MT. I'm going to skip over that in the interest of time, but how practical is the strict unsupervised scenario? So one thing that I definitely can say is that a lot of the techniques that are used in unsupervised MT are practical in semi-supervised learning scenarios where we have a little bit of training data. So we can either train the model first with an unsupervised method and then fine-tune using the parallel corpus, or train the model using a parallel corpus and update with iterative back translation. And part of the reason why it's why this is particularly good is there's very few languages in the world that don't have any parallel data but have lots of monolingual data. For example, almost every language in the world has parallel data from the Bible, if it has any amount of monolingual data. But the Bible is very out of domain, very small. So because of that, using that to seed a model, but then doing almost unsupervised translation seems like a practical way to do like news translation or something like that. And then another area where these techniques are practical is if you have a task where you like legitimately cannot get very much data whatsoever. So one example being style transfer from like informal to informal text where there's not very much data, especially in different languages. Another example that has been used recently is translation between Java and Python. For example, where there's like lots of Java, lots of Python, but very little, very little parallel data. There's some parallel data, but not very much. So yeah, the discussion question is pick a low resource language or dialect. Research all of the monolingual or parallel data that you can find online for it. Would unsupervised or semi-supervised MT methods be helpful, and how could you best use the existing resources to set up an unsupervised or semi-supervised MT for success on this language or dialect? And this is a reference to a paper that you could take a look at to discuss that. So cool. Any questions before we start the discussion?